Okay, welcome to this lesson on Lewis dot structures. Okay, um, this lesson you're going to need a couple things. You're going to need this note that you're seeing in front of me here, in front of you, on Lewis dot structures. But you're also going to want to have the new copy of the periodic table that I sent out that looks a lot like this one. Okay, it's a PDF, and so you'll want to open that up in a PDF, and you can have access to both of them. I will be looking at that, and it's important that we use the new periodic table that I sent you today, not an older one. Okay, so that's a kind of important concept. Okay, so so far we've been working on drawing atoms, and it's kind of a fun process, not overly difficult, but a little bit labor intensive. So quickly, so let's go through here. Scientists quickly realized that um, drawing Bohr-Rutherford diagrams was a bit labor intensive. Not something that most high school kids enjoy doing either. And atoms, so drawing Bohr-Rutherford atoms was time consuming and somewhat difficult. You know, I don't know if I'd call it difficult, but maybe not the best word for it that I use there, but it takes a bit of effort, and there's a lot of little pieces and bits and pieces, and they didn't need to know all that. They also determined that electrons in the outermost orbit, okay, so the electrons on the outer shell, the outer energy level, outer orbit. Notice how I use three different words there: shell, orbit, and energy level. You'll hear all of those used interchangeably. Unfortunately, add a third one in there. They were the electrons that were of greatest interest. They were the ones that were involved in what the atom was going to do and how it was going to behave. So they had the most interest in them, and so they named those electrons that were in the outer energy level valence electrons. And you're going to hear this term as well. So I'm adding some new terminology here: valence electrons, electrons in the outer shell, right? And valence electrons equals, just really simple definition, valence electrons equals electrons in the outermost energy level or orbit. And if I really wanted to, I could even add the word shell on here, because sometimes you hear them talk about it in those terms. So don't be shocked if you hear that down the road. Now, in the early 1900s, a scientist by the name of Gilbert N. Lewis, okay, he devised a simple way to draw atoms. So they wanted to simplify it. They felt that the Bohr-Rutherford model was just way too complex. Sit there drawing constantly everything. And when you started having drawing lots of them, it was crazy. So he devised a simple way to draw atoms that only showed up to 8 most valence electrons using dots. Didn't even use E's and minuses and all that stuff. He just used dots to represent the electrons that were evenly placed around the symbol of the atom. So what I'm going to do is I'm going to kind of show you that, those words, they sound fancy, but let's be honest, it's really quite a simple way to do this, okay? So if we wanted to do the draw, for example, two different uh, atoms that have this using the Lewis structure. And you're going to see this is really quite simple. Um, remove some of the underlining here. It doesn't need to be there, just kind of confuse us. And then we're going to turn my pen on. Now, before I do, I need to go look these up in the periodic table, because I got to figure out how many electrons are actually in the outermost shell or outermost energy level. Okay, so I'm going to go to my periodic table, and it's not really super big here, but we can zoom in on it a little bit. And what you'll find is that strontium is located right here. I'm not sure if you can see that, but I'm moving my hand around it right there. I don't need to see the numbers, nothing. I can just see SR, I'm in good shape. And what I can see is each of these lines represents an energy level. So 2 electrons in the first energy level: 1, 2, 3, 4, 5, 6, 7, 8 in the second, 1, 2, 3, 4, 5, 6, 7, 8 in the third, and then this one, whoa, it's all the way up to 18. Okay, and then this one here has another 18. But I don't really need to worry about that with Lewis structures. I only need to worry about the very last energy level. And I only need to worry about the last 8, okay, if I want. In this case, strontium has 2. So I can write those 2 on strontium, okay? Now, generally speaking, that's all I worry about. Don't have to worry about all these other electrons, just the 2, 1, 2, okay? If I was dealing with titanium, 1, 2, 3, 4 potentially, right? If I was dealing with another atom here, I'll count them out. So if it was nitrogen, it would be 1, 2, 3, 4, 5, okay? It would have 5 electrons. So let's go down here and draw strontium, okay? So how do I do that? Well, I turn my pen on and I write a dot here and I write a dot there. And I say there's 2 electrons. And generally speaking, I write 1 on each side. Sometimes I get scientists that will do this. They'll write them here like this. They'll go, well, strontium's got 2 and we're just going to put them together. And that's okay. My preference is to see them on opposite sides, but sometimes they do come together on one side. The electrons are movable, so they can move around. Sometimes we even see scientists write them like this, where they write 1 on the top and 1 on the bottom. It's really not that important where they are. The important thing is that you have 2, and usually they're kind of evenly spaced around the symbol to represent that even spacing that would be used in a uh, atom if it were in an orbit. We would have them evenly spaced around the energy level. Okay, so if I go to Xeon, Xeon's another one that's wow, it's like crazy, like nuts. Let's go to the periodic table. Where's Xeon? Xeon is way over here, okay? I know where these guys are because I picked them, so I'm on top of it. Well, Xeon is at the end. He's full, completely 100% full. That means all 8, the last 8 are completely fulfilled in, okay? So what I do is I'm going to draw it with 8 electrons completely in his outer shell, okay, or outer orbit, energy level. Notice again, I used all 3 words, shell, orbit, and energy level. They all mean the same thing, okay? So here we go. I usually go like this. I go 1. This is how I place them in order. 1, 2, 3, 4, 5, 6, 7, 8. And I did it purposefully in that order because that's the order that I generally start placing in um, electrons around an element. So if I have to do, say, for example, I don't know, say I have to do oxygen, okay? I'll just do oxygen. Let's do it. Like, I mean, it's not that hard. I got room over here. I'll draw oxygen. The symbol for oxygen is O, okay? Nice big O, okay? Then I got to go look at the periodic table, look for oxygen. Oh, oxygen's right here. It needs 1, 2, 3, 4, 5, 6. So let's pretend I'm going to do it, and then I'm going to place them onto my oxygen that way. So I almost always start, for some reason, here on the right side. 1, 2, 3, 4, 5, 6. So I'll have 2 on each side if I'm full like this, 1, 2, 3, 4, 5, 6, 7, 8. And if I'm 6, 2 of them are going to be empty. Now, it doesn't matter if these 2 are empty or these 2, but what would be wrong is to do something like this. This would be wrong to draw it like 1, 2, 3, 4, 5, 6. That would be wrong. We don't do that, right? 1, 2, 3, 4, 5, 6. No, we don't do that. We space them around the symbol in that manner and always pair here, a pair there. So 2 potentially here, 2 here. You could have 2 there and 2 there to fill up the 8, okay? Now, part of your homework is going to be, and I've just done one for you, if you see here, what part of your homework is going to be to draw all of the first 20 Lewis dot structures. They're pretty simple to do. You might get that done in all of like 5 minutes, right? And now you have to go look at the periodic table and check them out and whatnot, but that's okay, right? Okay. This method was called the Lewis dot structures. Okay, so they gave it a name, and they named it after the guy who kind of came up with the idea, and that seems fair. I keep thinking one day they're going to name something that the Lou something or the Lewinstra something, but I don't know if I'm smart enough to come up with my own idea. And it's currently the most common way to draw atoms. I was talking to my son the other day, and he's in university taking engineering, and he could barely remember drawing um, Bohr Rutherfords, but he clearly knew the Lewis dot structure system because he still uses it in his engineering courses. So, you kind of, that Lewis dot structure or the Bohr Rutherford stuff, that kind of will pass away. And what we'll end up doing is we'll just be focusing on using these Lewis structures moving forward, just because they're so much easier to use. Okay. All right. Now, a couple things that are extended from this, okay, that you can use and that we discovered was what was also discovered was that the atoms of the same family, i.e., column, because a column is a family, also have the same number of valence electrons. Okay, so let's take a look at the periodic table. What does that mean? Well, that means that all of the elements in this particular column have the same number of valence electrons. They have one, two, three, four, five, seven. And even here, these guys are one short of being full, so we write them as seven, even though that is not how it appears there. Okay, all right. You might think, oh, we're going to put eight there. No, they're one short of being in the final thing. So that's what happens. All right, let's move on back to the lesson here. Ignore the phone call, and here we go. This also meant that oh, no. Okay, so it says here that's also meant that elements in the same family would combine with other elements in similar manner, and they also tend to form the same ionic or same charged ion. And there's going to be a little more on this as we go down, but what you tend to find is that in a column in the periodic table, they all have the same properties and they form the same ionic charges. Okay. All right. So let's move on here and take a look at this. Okay. So all members of the alkali earth metals, okay, family form positive 2 charges. Okay, that is very common. If I look at the periodic table, these guys all here all will form +2 ions because they have 2 electrons in their outer shell. And essentially what they do is they give them up. They say, well, let's get rid of them and we'll become a +2. Give away 2 electrons, you actually become positive. Okay, and let's take another look here. And the halogens, the members of the halogen family, they form -1 charged ions, okay? They form -1 charged ions. And where are the halogens? Well, the halogens are here with fluorine, chlorine, bromine, all there. And they all form a -1 charge, okay? And I'm going to show you, we're going to zoom in on the periodic table here in just a second, and you'll get a better look at how this works. But just before I do, I said many periodic tables include the most common charges for the elements in the periodic table. So I mentioned at the top of the show is you got to make sure you have one of these periodic tables that actually shows the most common charges. So I had to go and make sure I had one of these in our textbook. Unfortunately, if you have a textbook, the back of it has a beautiful periodic table that looks a lot like this one here that I'm showing you, okay? And you'll see how this operates here. Now I'm going to zoom right in. First, I'm going to zoom in on this here because this gives you a sample, and then we'll take a look at some of the specific ones, okay? So look at me zooming right in here, and I'm looking at this sample. This is a sample of iron in the periodic table, okay? And what you see here is that this is the atomic number. This is the most common charge of iron. Iron is most likely to form a +2 charge. And the next most likely charge it might form is +3. So iron's one of those special ones. Not very many are like this, but some are. They will form two different possible ions, a +2 or a +3. So that means it's actually given away two or possibly given away three electrons. Okay? Our symbol, Fe here, the name goes in here, and then finally we have the average atomic mass, okay? And these are all written here and explained right here in the middle of this periodic table. If you get a chance to print this and you can get it kind of blown up, that's great. If not, like look at how I'm able to on the computer just zoom right in and check it out. So let's look at a couple more of these elements in the periodic table. There's iron right there. There's where it actually sits. There's chromium. Chromium's right couple over, 20 atomic number 24. Most common charge is 3. The next most common charge is +2, so +3 and +2. There's the spelling of chromium. There's its average atomic mass, and of course, its symbol right there. And we can do this with any of the elements in the periodic table, right? They're all over here, right? So for example, here's zinc. Zinc forms a +2 charged ion. Zn is the symbol. Atomic number is 30. By the way, the atomic number also tells us the number of protons. Okay, gives us a lot of information about this particular atom or this particular element. An average atomic mass. Okay, and of course the spelling of the word zinc. And we can see some pretty funky ones down here at the bottom as well. Like, oh, look at this one, like gold. Gold is number 79. It'll form a +3 or a +1. And it's AU for some reason. Don't ask me why it's not GO. It's just AU, and the average atomic mass is 196.97. And you'll notice that generally speaking, not always, but almost any column I look at, like look at this one here. Oh man, rhenium and technetium are both +7s, and that's not uncommon. That ones that are lining up in the same column often have the same charge, but not always. You'll see manganese, which is at the top, it has a +2 or a +4 potential charge. So it's not always completely consistent, but there is usually some level of consistency. Here, for example, +6, +6, a +3, and a +2 for chromium. So they vary depending on what they do. So these two here, molybdenum, and I think that's tungsten. W is tungsten, yes. Tungsten and molybdenum share the same charges. So it's not 100%, but it's pretty consistent. The bottom line is you're always going to be relying on your periodic table. You're going to want to look at it. Having a printed copy of it is really useful, okay? If it prints out and it's not readable, you need to be able to try to find a way to get it to print on a little bigger page and go that way. Yeah, at school we usually have one. I struggle as an older person, okay? Because like this text is pretty tiny, so this works out really good for me, okay? All right, so that wraps up the lesson on Lewis dot structures. You're gonna get a chance to draw the 20, and then there's a few questions at the bottom here that you can work on as well. Okay, I really hope you get it and you're able to draw all 20 of these. We'll try and take them up in class at some point. All right, enjoy your worksheet.